Now let's talk about some of the more basic operations we can do with matrices and vectors. And these are addition and multiplication of matrices and vectors. To start out with addition, addition is very simple. For two matrices, A and B, that are both m by n, and it's important that here A and B have to both be the same size. In this case, A plus B equals a new matrix C, which is the same size as A and B. And the ij entry of C is just the ij entry of A plus the ij entry of B. All we're doing is we're taking these two matrices, we're adding up the corresponding elements, and that is the matrix addition. Now it's important that because of this definition, addition is undefined when A and B are different sizes. So if A was m by n and B was some other size, p by q, we could not write A plus B. We can't do that. We can only add matrices or vectors that are the same size. Matrix multiplication now is a little bit more complex. Matrix multiplication is not the element-wise product of the corresponding elements. Rather, it's defined as follows. For a matrix A in R m by n and B in n by p, and these sizes are very important here, which we'll come back to in a second, the matrix product A times B is a new matrix C with dimensions m by p. So the number of rows in C is equal to the number of rows in A, and the number of columns in C is equal to the number of columns in B. And one way to remember this is that for matrix multiplications, let's write out the two sizes here, m by n and n by p. And what happens is that the inner dimensions have to match. They have to be the same number of columns in A as rows of B. And then the final matrix is the size where we just ignore these things. The inner dimensions disappear, and the final size is the number of rows in A and columns in B. The definition now of the ij element of this product is the sum from k equals 1 to n is the number of columns here and rows here, of aij times bkj. And what this is saying is that if we take our matrix A here and our matrix B here, we look at the ith row and the jth column, ith row of A and the jth column of B. We take all their corresponding elements, we multiply these together, and then add them all up. And this makes it obvious, hopefully, why the number of columns in A has to equal the number of rows in B. We need to have these corresponding elements here, or this sum wouldn't make any sense. Now, an important point is that because of this definition, multiplication is going to be undefined when we don't have this property, when the number of columns in A doesn't equal the number of rows in B. So if A and B were different sizes, say A was still m by n, and B was p by q, then we could not write A times B. Do not write this. As with all rules, though, there is one exception, and this is an exception because it makes life much easier. If you have a scalar value C, and C is just a scalar value, it's a value in R, then we do allow ourselves to write C times A when A is still just some arbitrary matrix, an m by n. Now this is not a valid matrix multiplication, right? Because C here is really a 1 by 1 matrix in some sense, and that would not be a valid matrix product. And what's happening here is we actually take this to mean not a matrix product, but rather we're just taking every element of A and scaling it by C. But this is the one exception where we are allowed to write a product that does not obey the rules of matrix multiplication. Other than this, we have to have this property, or matrix multiplication is not defined. Now there are some important properties of matrices and matrix multiplication. The first important property is that matrix multiplication is associative. That means if A, B, and C are defined this way, this is basically defining A, B, and C, such that we can compute all these different products here, or rather the product A times B times C. In this case, A times B times C, if we do this operation here first and then multiply by A, is the same thing as first multiplying A times B and then multiplying by C. It doesn't matter the order in which we do these operations. And so for that reason, we won't even bother putting parentheses around here, and we'll just write this as A, B, C, because it does not matter what order we do them. Matrix multiplication is also distributive. What that means is that, again, for properly sized matrices here, these are sized so that we can compute the product of A times B or A times C. Notice that these are actually different sizes from the ones above. But in this case, B and C are the same size, so we can add them together. And the product of A times B plus C, we can distribute this product into the addition. So this equals A times B plus A times C. Lastly, though, and very importantly, matrix multiplication is not commutative. What this means is that if we have A times B, this does not equal B times A, as it does in the scalar case. And this is actually wrong in several ways, right? Because if A, say here, if A is m by n, and B is n by p, then we can form A times B. The dimensions match here, so that is a valid matrix product. We cannot, however, form B times A. The dimensions here, unless P equals M, but we'll assume it won't, we cannot even form this product. So these, of course, cannot be equal. But beyond that, even in the case where we could form all these products, say if A and B were both m by m, this property would still not necessarily hold. And in fact, in most cases, you'll see it will not hold. So unlike scalar multiplication, matrix multiplication is not commutative.